Right, good morning everyone. Hopefully you can all hear me. Welcome back for day 2. Thanks for coming back. Just to remind you today, if you do have any questions, please post them to the S3 channel for normal distribution. Gavin and Elaine will be on hand to answer your questions on Teams. I'll also be about looking at those questions on Teams as well. So if you have got those queries, please let me know and that'll help me know if there's anything that I need to maybe go over in a little bit more detail. Now, hopefully you've had a look at this starter question. So this isn't related to stats, but this is just trying to keep you going with these pure questions, so keeping up on track with that. So this question here, we're given that y equals 2 to the power of x, and we're going to write all 3 of these questions that we've got, we're going to write them all in terms of y. So the first one, all I'm going to do is just rewrite this as 2 to the power of x squared. So remember, one of your rules of indices, when you've got the brackets there, you can multiply the powers if you wanted to work that back. The reason why I'm going to do that is I can simply just rewrite that to the power of x as y. So this just becomes y squared. The second one, I'm going to rewrite as 2 to the power of x to the power of 3. That's something I can just simply work out. That's just going to be 8. So another way of writing 2 to the power of x plus 3 would just be 8y. Then we have the last one. Now this is 1 over 4 to the power of 2x minus 3. But what I'm going to do first is just think about what 4 to the power of 2x minus 3 would be. Now this question is 2 marks, so there's going to be a little bit more work to do than the other two. There will be a number of different ways you could do this. This is just one of the ways you could do it. So the first thing I'm going to do is rewrite the number 4 as 2 to the power of 2. And this has all been taken to the power of 2x minus 3. Now remember, I want to try and get this in some sort of form of 2 to the power of x, because that's what y is. So with this, I can multiply these powers and I get 2 to the power of 4x minus 6. Okay, I'm just multiplying the 2x minus 3 times the 2. This can now be written as 2 to the power of 4x times 2 to the power of minus 6, using a similar rule as we did in part B. And then 2 to the power of 4x, well, that will just be 4 to the power of y, because that's just 2 to the power of x, all to the power of 4. And then 2 to the power of minus 6, that's just something you can do in your calculator. Okay, it's just 1 over 2 to the power of 6, so you can just simply put that in your calculator, and we get 1 over 64. So that would just be y to the power of 4 over 64. But that's what 4 to the power of 2x minus 3 is. We're asked for 1 over this, so we just get 64 over y to the power of 4. You could also write 64 y to the power of minus 4. That would also be an acceptable answer. So that was just a little recap on some pure work that we've done before. Now what we're going to do is move into our main topic today, which is critical regions. Okay. Now before I get started with the first example, I'm going to give you a little bit of a scenario just so you can understand a little bit more about the critical regions and maybe go over a little bit of hypothesis testing that you might want a little bit more details on from yesterday. So I'm going to give you a scenario. A manufacturer makes sweets in bags of 500 grams. The standard deviation is 10 grams. So let's say we take a sample of 100 bags. This means that N would be 100. Okay, so we've got a manufacturer, they make thousands, tens of thousands of sweets every day. They say on the packet that the weight's 500 grams, and we're told that the standard deviation is 10 grams. Obviously, to work out the mean of all the bags, that will be a very time-consuming process. We might just want to take a sample. So we're just going to take a sample of 100 bags. Now, if I was to work out the mean of that sample, it's unlikely that I'd get exactly 500. Now, if the mean truly is 500 grams, I should get the sample should be quite close to that if the mean truly is. You wouldn't expect to find many samples where it's quite far away from that mean. So let's say we just take a sample of 100 bags. Now, if we want to work out the sample standard deviation, so we learnt yesterday, a little bit of a recap from yesterday, that the sample standard deviation can be worked out by doing sigma over the square root of n. You could also think of this as the sample variance as sigma squared over n. The bigger the sample we take, the smaller that sample standard deviation is, because the bigger the sample we take, the closer we should actually be to the mean. Now in our example, sigma we're told is 10, and n is just the number of items we have, the number of bags that we're taking in our sample, which is 100. So I do 10 divided by the square root of 100, and I get 1. Almost like I picked nice numbers for this to work out as 1. So we looked at earlier that, so right at the start of the booklet, you learned that 68% of data lies within one standard deviation away from the mean. So what this would mean in this case is we'd expect from this sample 68% of the samples we take would be between 499 grams and 501 grams. That's because in this case one sample standard deviation is just 1. So we're not surprised. We'd expect most of the samples we take to be between 499 and 501. But what about 498 to 502? Let's just widen this range a little bit. Now, again, if we go back to the start of the booklet, we learnt that 95% of data lies within 2 standard deviations away from the mean. So 498 is 2 standard deviations below the mean. 502 is 2 standard deviations above the mean. So we'd expect, out of all the samples we take, we're not surprised if we find samples that are, if the mean truly is 500 grams, we're not surprised to find samples that are between 498 and 502. But beyond that, it's quite unlikely, if the mean truly is 500 grams, that we'd find a sample that is less than 498 or more than 502. In fact, there is less than a 5% chance that we'd find something that is less than 498 or greater than 502. So if we took a sample and got something that was outside of that range, then we'd have quite good grounds to question that mean of 500 grams. And this is where we're looking at the critical regions. In that example, we'd say if we wanted there only to be a 5% error, so 5% significance level, we would be saying that anything below 498 or 502, we'd have grounds to reject the null hypothesis. Okay, so our critical region would be reject anything that's less than 498, except anything that's greater than 502. So let's get into the examples, and we'll see how we set up a hypothesis test when we're looking at the critical regions. So this is linked into what we were doing yesterday, but it is another way of being able to work it out. And sometimes in the question, it might just ask you to give the critical region, or the question might give you the critical region, and then you have to make a conclusion. So in this example, we've got a mean of 0.580 and a standard deviation of 0.015. Okay, in the questions, you should always be given the standard deviation for these hypothesis tests. The machine is serviced and a random sample of 50 bolts is taken from the next production run to see if the mean diameter of the bolts has been affected. Now, when it says has been affected, this is really important. This tells us this is a two-tailed test, because we're looking at the change in either direction. Either the mean, if it was a one-tailed test, we only look at the mean being greater than what it stated or less than what it stated. If it's a two-tailed test, we are going to reject H0 if there's significant change in either direction. So it could either be greater than the 0.580 or less than the 0.580. So if we're finding the critical region, what we need to recall, just like we did with correlation, is that the critical region is where we reject H0. And we'll see in the diagram in a second what that looks like. So the first thing that I do with a hypothesis test, I have to set up my hypotheses. So the null hypothesis is that the mean is what it states, it's 0.580. So that is your null hypothesis. That's what we believe to be true to begin with. Then our alternative hypothesis is that the mean does not equal 0.580. Remember, when it's a two-tailed test, we're going to put does not equal. If it's a one-tailed test, we'll either have a greater than or a less than sign. Then we need to write the distribution. So the diameter of the bolts, we're told in the question, is D. So I'm going to put D with a little line above it. I put the line above it because I'm talking about a sample here, not just normal standard normal distribution like we've been doing earlier in the booklet. So I put that line above it because I'm talking about my sample here. So I put the N for normal distribution. The mean is 0.580. It's always going to be what your mean in the question is as what you believe to be true before you begin. That's what you always put as your mean there. And then our variance is 0.015 squared. Okay, standard deviation is 0.015, so variance is 0.015 squared. And I divide that by n, which is 50. Now remember, that's my sample variance. If I want the sample standard deviation, when I put it into my calculator in a second, I need to put the square root of that. And I put the square root of the whole thing. But I'll show you that on my calculator in a second. So let's draw a sketch though, because I think it makes more sense what's happening here when we've got a sketch. So we believe the mean to be 0.580. Now, I've got a 1% significance level, but I'm looking for the change in either direction. So basically there's a 1% chance I could be wrong to reject the null hypothesis. But that 1%, I can split that error in either tail. So I can either split this at the bottom half, or I can split this at the top tail of this. Okay, so in each of these shaded bits here, each of these has an area of 0.5%. Okay, so I'm allowing that error of 1% to be at either tail, at either end. So the area here is 0.005, okay? That's just 0.5% turned into a decimal, okay? And I've got that 0.005 at either end. What I want to do is find the values here and here, where I've just shaded in yellow. I want to find these values here that I have to reject the null hypothesis because it's either too low, it's too far away from the mean. So now what I do is I get the calculator out. And what I'm going to first do is work out my lower tail. So on the calculator, I go menu and then 7. And now this time, unlike yesterday, I need to use inverse normal because this time I know the area, but I don't actually know the value that gives you that area. So on the calculator, you put 0.005 for your area. Your standard deviation is the square root of 0.015 squared, or you could just put 0.015 and not square root it, divided by 50. And then the mean is just 0.580. I put that in, and what I get is 0.5745. So my lower tail is going to be 0.5745. 0.5745. So what this means is anything lower than 0.5745 means I reject the null hypothesis. Anything lower than that is too far away from the mean. Now let's do our upper tail. And when I do the upper tail, so same process again, the only thing that's going to be different here, so my standard deviation will be the same, my mean will be the same, but for the upper area, I need to do 1 minus 0.005. And that's because on your calculator, when it deals with areas, it only tells you the areas to the left. So it won't know that you mean 0.005 to the right. Okay, we just saw what happened. We put 0.005 to the left. We got our lower tail. So we want that upper tail. We need to do 1 minus first, hit equals, and then we get our answer. So for the lower tail, it's 0.5845. So then we write down what our critical region is. And we reject H0 if D is less than 0.5745 or D is greater than 0.5845. Okay, and this would be our final answer for part A. Now that's where we reject H0. So any values that fall either below or above in that critical region there, we would reject. So let's have a look at part B. The mean diameter of a sample of 50 bolts is calculated to be 0.587. Comment on this observation in light of the critical region. So what we can say is 0.587. If I go back to my diagram here, let's put in that upper tail. Now we can see 0.587. This will lie somewhere up here. This will lie in the critical region. The critical region is where I reject H0. So because 0.587 is greater than 0.5845, it means I'm going to reject H0 as 0.587 lies within the critical region. Okay, and then I need to put a comment. So there is sufficient evidence to suggest the mean diameter of the bolts has been affected. The context is really key here. Having looked at some of the work we got in from yesterday, a number of you doing the right calculations, it's just that context. I know we're mathematicians, I know we don't like writing lots of words, but we do need to make sure that we write these sentences here. So the context is really important. It hasn't got to be an essay. Just look at the question, look at what that context is. Normally what I tend to do is just simply kind of copy the statement from the question and then just say whether I'm rejecting or there's sufficient or insufficient evidence. Okay, so I know you don't like writing sentences sometimes, but it is important that we do it. Right, if there are any questions on that first one, please post them in the Teams chat. So if there's anything you just want me to go over again, I will have a look there. I can't see anything at the moment, but I will keep checking. As I'm laying Gavin on hand to answer any questions. Okay, so let's go through the final two examples. I'll go through these ones a little bit quicker now. So now we've kind of learnt the process. So in this question, we've got a braking load with a mean of 1,000 newtons, standard deviation of 21 newtons, and we've got a sample that we're taking of 50. So when we are doing this, we're testing whether the mean braking load has changed. Okay, and it's that keyword changed that tells us whether it's a one-tailed test or a two-tailed test. So we write our hypotheses, as we always should do. The mean is 1,000. So our null hypothesis is that the mean is 1,000. The alternative hypothesis is that it isn't 1,000. Because we're just talking about changed. It's a two-tailed test. That change could happen in either direction. Then we write our distribution. I'm going to use x as my variable this time. We've got a mean of 1,000, a standard deviation of 21, so a variance of 21 squared, and we have to divide that by n because we're talking about our sample. So if I just draw a sketch to the side, we've got a mean of 1,000, and what I'm trying to do is find these limits here. Now in this question, I'm testing at the 5% significance level. So I split that 5% into 2, so 2.5% either tail. And that would help me what I put in on my calculator. So now what I'm going to do is going to find the lower tail, and I'm going to find the upper tail. So yeah, again, I'll get my calculator out here and show you what I'm doing this time. So for the lower tail, I put in area 0.025. I just put in the area as it is because it's telling me the area to, I want it to tell me the area to the left. Standard deviation is 21 divided by the square root of 50, or the square root of 21 squared divided by 50, whichever you prefer. And then we have a mean of 1,000. And we get 914.18. If I do the same with the upper tail, I get 1005.82. But remember, when you do it this time, you need to do 1 minus that 0.025. Okay, and you just get the following, as you can see there. Also, you probably hopefully can see the symmetry that these two values here are the same distance apart from your mean as well. So the critical region is that x is either less than 994.18 or greater than 1005.82. Okay, so that is our answer. It's important that you write it in the correct way. Don't write probability or anything like that because you'll lose that final mark if you do so. Okay, it should just be, you're just talking about the value, you're not talking about probability here. So it's a common mistake I've seen people make in the past, so just watch out for that. Then we're told that the sample mean in part B for the 50 pieces of rope was 103 newtons. So we took a sample of 50 and we got 1003 newtons in our sample. So if we look at our diagram here, well, we can see that 1003, where I've just put that red cross, does not lie within the critical region. So in this case, we'd say we accept H0. 1003 does not lie within the critical region. Lie within the critical region. So there is insufficient evidence to suggest the mean of the braking load has changed. Yeah, again, context again, reference the braking load, okay, or the tension. It's important that you use that key context that's given there in the question. Okay, yeah, again, let us know if you've got any questions. If not, we'll move on to our final example, and then you can go away and have a look at some of the questions that were given you in that assignment. So our final one, yeah, again, I've done what I did yesterday and changed the marks on one of these. So in the old spec, you would have got 4, but really, because you can use your calculator, it's made it a little bit easier for you. So I'd say it's probably only 2 in our new spec. So we've got a random variable y is normally distributed with a mean of mu and a variance of 12.25. Two statisticians carry out significance tests of with a null hypothesis of a mean of 63, an alternative hypothesis where the mean is greater than 63. So a statistician, got there eventually, uses the mean y of sample size 23 and the critical region for his test is y is greater than 64.20. Find the significance level for A's test. So first thing I'm going to do, I'm using y as my variable this time, and I'm talking about sample, so I'm going to put the line above it. And I've got my mean of 63, because that's the null hypothesis. The null hypothesis mean will always be your mean here. And then the sample standard deviation, well, the variance is 12.25. Sorry, it's the sample variance. So it is the variance is 12.25. So the sample variance, divide that by n, divide it by 23. Now, what I'm trying to do is work out what is the probability that y is greater than 64.20. Now, just do a sketch to the side and show you why I'm working that out. If I've got a mean of 63 and the statistician is rejecting the null hypothesis if the sample mean is greater than 64.2, well, we need to find the probability of finding a value that is greater than 64.2. That percentage, or that decimal, will be our significance level, okay? Because our significance level, that's where we're going to reject. That's the chance that we've wrongly rejected the null hypothesis. So on my calculator this time, I'm going to use normal CD. I've got a lower limit of 64.2. And I've got a big upper limit, okay, because it's just going to, normal distribution is just going to go on infinitely. And then put in my standard deviation, so it's the square root 12.25 divided by 23. And my mean is 63. And as you can see here, I've got a probability of 0.05006 essentially. So I'm just going to, if I go to three significant figures, or two significant figures, I can see that it's going to be 0.05. Okay, so that's my significance level. Okay, that's the probability that I reject H0. So that will be my actual significance level. Okay, and 5% is quite common, so that makes sense to us here. So then part B, or part 2, we're told that the statistician B used the mean sample of size 50 and significance level of 5%. Find the critical region for B's test. So in this case, we write our distribution again, but now we're going to divide by 50 instead. So in this case, what I'm doing is actually trying to find the critical region. So this time it's just a one-tailed test. Okay, I've already got my hypotheses given to me in the question, so I don't actually have to write them out again like I normally would. So it's just a one-tailed test this time. So this time I am just looking at an area of 5%. However, if we draw the diagram again, we've got a mean of 63, and we're rejecting anything above here. So I need to find out what this value is here. But with a 5% level of significance, I've got an area here of 0.05. So on my calculator, this time I know the area. So when I know the area, I want to use inverse normal. And you want to do 1 take away 0.05 for 0.95. Okay, because remember, you don't want that 5% above it. You'd calculate, we'll talk about the 95% below it. And then we've got square root of 12.25 divided by 50, mean 63 still. And we can see that we get 63.81 to 2 decimal places. So what this means is the critical region is 63.81. So I am rejecting anything that is greater than 63.81. And that would be my critical region. Now, we've given you some questions. So to the right of the screen, you can see the questions that we want you to do today. So this is a mixture of some of the ones from exercise 3G and also the mixed exercise as well. On the assignment, you should see the ones that we want you to submit, but make sure you are doing the rest of the questions well. Don't just do the ones that we want you to submit. It's important that you're practicing a whole wide range of this. Also important that you ask us questions. Me, Lane, Gavin will be on Teams to answer any questions you've got, so please do ask away. There is a start question for tomorrow. So there's a start question tomorrow based on normal distribution. So have a go at that before the lesson, and I'll go through that answer tomorrow. Tomorrow we're going to start S4, so that's the next booklet. So you should be able to find that the notes for that on Teams. So if you want to read up in advance, you can do. And there's some questions there as well. So we're going to start S4 tomorrow. So further look at probability, look at probability and some Venn diagrams. Hopefully some of that should be a little bit easier compared to this. It should be a little bit of a recap of GCSE, but still important nonetheless. People can make mistakes with Venn diagrams. So for now, have a go at the questions today. Make sure you submit them. I can see a number of you have already submitted yesterday's, which is excellent, and some of you already submitted today's as well, which is fantastic. So keep doing that, please. Make sure it's all in for the end of the week. It's important that you keep learning in this process. Ask us questions. That's going to be it from me. And I'll see you on here tomorrow at 11 o'clock for probability and Venn diagrams.